One of the uses for the JK flip-flop is frequency divider. And during this demonstration, we're going to take a look at that use of the JK flip-flop. Right, so now we have okay, I'm going to erase that for now because I'm getting ahead of myself here. Here is a pretty much raw JK flip-flop with already some of the sources connected to this. So now we have, let's just preset ourselves with everything that we need to have. Okay, set and reset, they have to be, they are active high. So if we bring this set to high, we're going to have hard set, and Q is going to go high no matter what happens everywhere else. So we don't want that. We just want this thing to be not active. And also we don't want this reset to be active. We don't want that to be active. We want this thing to be inactive. So when these both inputs, reset and set, are sitting at or tied low, which means if they're active high, they are not high, which means they are going to basically be almost as non-existent as far as functionality. They are going to let this synchronous inputs take over the whole operation. All right, now we're going to have to establish something that's called a toggle position. So we're going to set both J and K high. So this one's going to be high and that one's going to be high, which means when we apply clock, every positive transition of this clock input, input, those outputs, Q and not Q, they're going to flip the state. So if this one is 1 and this one is 0, they're going to exchange. This one's going to become 0 and this one's going to become 1. All right, so they're the opposites, and it's just going to flip and flop between each other every time there's a clock when both J and K are sitting at high. All right, now let's grab ourselves a clock generator. Okay, now that is sitting somewhere here. I'm going to go place, component. You know what, we already have the ground selected. It's under sources and power sources. Here's ground. Click, we're going to need that. So I'm just going to place it somewhere aside, and then we're going to get ourselves a clock source, and that's under sources, but that's under the digital sources. And when we click that, we get the sub menu of what kind of digital sources we can have. This is the interactive source, which is that one here. No, that's not what we want. We want a digital clock. That's what it is. Here's the symbol of that. So we're going to click OK and just place it on the side here for a second. For the time being, let's close this menu right here. Okay, so let's just clear up the display of that. So you either right click and call properties, or you can just double click on that device to call up these properties. Now the frequency of this clock says it's 1 kilo. You can change that to, like, say 5 kilo if you want. So it's 5,000 hertz, and you see that is going to, but you know what, let's just leave it at 1 kilo. Okay. And display, let's clear up the display here. We don't want the labels, we don't want to see any of that. Values, yeah, we can see, we might want to see that clock here, the frequency of that. And because we already set the value to 1K, but we haven't clicked OK yet, so this still old value shows up. That is there, labels, okay, click, okay, and all the other things disappear, and we know that this is 1 kilohertz. Now, because it's a digital clock, what is a digital clock source in multisim? It's a astable multi-vibrator. Basically, it's an oscillator set up in such a way that it oscillates between 0 and 5 volts. That's the one, that's the condition of that. It's just so it's easier for us. We don't have to tweak with any other equipment. We can call up a AC source and set it up that way. But for our convenience, we already have the digital clock. Now let's confirm the waveform. I'm going to grab a Tektronix oscilloscope. There it is, right? And I like to grab that one for our purposes because this is the one that we have in our labs at our school. All right, so we're going to place it somewhere here, and right away we're going to connect the ground. See, we just had this thing sitting aside for waiting for us to be used, and we're just going to connect right to the ground terminal of the oscilloscope, and then straight up we're going to go from the output of the digital clock right to the channel 1. Right? Double click on the scope to call up the oscilloscope on the screen, and we're going to have to turn that on right here. Okay, now let's start simulation, see what shows up on the screen. Oh, something is showing up. We get some kind of a signal going. Let's make sense out of that, bring it to the controllable visually position and shape. All right, so volts per division, it doesn't change the signal, it just changes the way the signal is displayed on the oscilloscope. So we got this thing to some sort of comfortable height. So you see here, position. If I change the position of channel 1, because this is channel 1, you see here, and this is the channel 1 controls. This is channel 2 controls, and 3 and 4. This one is a 4-channel oscilloscope. All right, so now we can position. You see here, see the little arrow that shows us where the 0 sits at. Okay. Channel 1 menu, so we're DC coupled. If we go AC coupled, which means we're going to bypass the DC component of it, see this this signal goes high and low, and the high is above the 0 line and the low is below the 0 line. But this is the AC component displayed only, but sometimes we want to isolate the AC component, but not in this case. We're going to toggle the coupling. Basically, it's the way it's coupled into the input, into the DC, all right, which means it's showing us the true signal. Right? Sometimes the whole signal is 100 volts DC, and then there is maybe a 5 volts ripple. So in order to see that 5 volts ripple, you want to isolate that from the DC component so you can actually see the shape of the ripple. But in this case, 5 volts from 0 to 1, sorry, from 0 to 5, 0 to 1 logic, the logic condition. We want to have this thing DC coupled. Now let's stretch the time per division. So right now it's 2 milliseconds per division, and it's showing us the signal too dense. Let's just magnify the way the signal is displayed a little bit so you can see it more comfortably, and we're going to change the time per division, so it's 200 microseconds per division right now. And basically what else we need to do with that? We need this thing to stop scrolling. How do we stop this thing from scrolling? We're going to change the trigger level. Let's go call up the trigger menu. All right, so trigger is the edge, so it's recognizing the edge of the signal, and rising edge. Okay. Mode automatic, it's not normal, so it's auto, so that's fine. It's automatically recognizing the signal. And let's see, we can just change the level at which the oscilloscope can actually lock on to that signal. Right? So this is going to change. This 0 reference is going to stay, but this is the trigger level. This is when the oscilloscope is recognizing a solid signal. So let's move that a little bit up. See if we can make it stop. All right, look at that. Now the scope can sense the signal and can lock onto it nice and solid. All right, so that's good. So we can see our signal. Now, it should be 1 kilohertz. Can we see the whole period on this? Yes, we probably can, but we can reposition that so we can see at least one repetitive waveform. So let's say from here it goes up, here, down. Okay, so from here to here, it's a whole waveform, for example. Right? Goes on 0, goes up, and goes on 0. So from here, the signal starts repeating, from here to here. Okay, let's do a measurement. All right, call up the measure facilities on this scope, and the menu shows up. We are measuring channel 1. Good. channel 1 type. Okay, here's channel 1 source, channel 1. Okay, type, what do we want to measure? Once we choose the quantity we want to measure, we're going to have these little guys light up, which means that they're going to be our controls. I'm going to call up the cursor. Cursor, there we go. Cursor, type. We have the source channel 1, the type of the cursor. What do we want to measure? Voltage? No. Click again. Time? Yes, that's what we want. That's what we want. So you see these little two lights lit up. This is going to give us one cursor, and that is going to give us the other cursor. We can control the positioning of the cursor. So let's see where the signal begins. All right, somewhere here. Okay, so we just got that cursor where the signal begins. Some sort of a common point that we can identify, and let's call up the other cursor to see this where the signal starts to repeat, and we found out that it repeats right here. So let's just bring that cursor to that point. Let's just align that with that. But can we do that or not? There we go. All right, now yeah. No, of course it's not. It repeats right here. Okay, that's where the signal begins to repeat. All right, from here to here. Let's bring that cursor right there. All right, there we go. And what does it show? It shows 994 because I wasn't able to point at exactly, get this exactly to this point. Can we do that? There we go. That's we're aligned with this point and with this point, and this shows the timing reference from 0, cursor 1, cursor 2, and the difference between those cursors in timing gives us the calculation of 1 kilohertz. Good. All right. So now we know that this thing works and it does what it says it does. All right. Cool. Let's just turn the display off for a sec. Stop the simulation. Disconnect that and put the scope aside a little bit. Oh, it just keeps dragging the ground with it. Okay, so now let's connect this clock source where it belongs to the clock input. All right, let's bring it somewhere here, and we're going to make a connection just like this. Now we're going to bring up the scope into the picture. The ground just keeps being dragged. There we go. Can we make a nice and clean connection here? Yes. So channel 1, we're going to connect to the output of the clock source. Right? And channel 2, we're going to connect this to, let's see, that way, make it nice and clean. There we go. We're going to connect it to the Q output. Right? So let's just analyze what is going to happen. The clock is being applied, and this is a positively edged triggered clock. So something is going to happen. This output is going to these outputs are going to change every time a positive clock is being applied. So here, things are going to change. Whatever it was, it's going to be not it. That is going to be it. All right. Now, over the whole cycle, nothing's going to happen, and then when the next cycle begins, it's going to toggle again. So every time this thing goes up, something happens, and it stays that way for the whole cycle. So here's a toggle, cycle, toggle, cycle, toggle. So every time there's a toggle, and there's a full cycle, we are losing the whole cycle before we get it back, which means that this frequency is going to be the half of that. Let's confirm that on the oscilloscope. Double click, call up the display, turn it off, turn it back on. Oh, it's still there. Anyways, we can make sense out of that. Start the simulation. And let's just call off the measurement. Of course, we still have the same signal here, right? Let's make it a tiny bit smaller on the display so we could fit other signals here. And position a little bit up. And I'm going to position that in between those division lines, so on the computer monitor you can actually see that. I know you can barely see it probably. So here we can see the signal, all right? And here's our ground reference, all right? Now, no, sorry, here's our ground reference, here's our trigger, right? Level. Now, let's see what's happening on channel 2, because we have that connected to the Q, all right? So this should be half of the frequency. Let's make this a little bit tighter so we can see a few cycles of that, right? Turn on channel number 2. Oh, look at that. Let's bring it up to some sort of a viewable condition. So let's make that smaller here. And look at this. We're going to position that so it's more visible. Oh, here's the channel 2. Look at this. Does it look like this frequency is half of what the input? So here's our Q, and here's our input to our clock. All right, look at this. Every time the clock goes up, there's a toggle here. So the Q goes off, and the Q goes back on when there is next time this clock is up. And then it goes down again, so it's off half times as slow as the clock, or on. Can we just reposition that so we can see the on times? Yeah, there you go. Yeah, but now let's see if we can trigger that from channel 2. Right? So here's how we call up the trigger menu. And instead of taking the samples from channel 1 to make the whole thing settle down, let's take a sample from channel 2. And now we have, the scope likes it better. So this has settled, both signals have settled down. All right, so on half as much as the input, right? So here's on, positive edge, and the positive edge changes, but it's off. And it is on again. We have to wait 2 cycles. So we have to wait 2 cycles before it completes 1 cycle. So this frequency is half of this frequency. So hey, you know what? This JK flip-flop divided the input frequency by 2. So it's half of that. Let's take it slightly bit further. I'm just going to push that aside for now. Stop the simulation, and let's just go crazy, shall we? All right, so what I'm going to do, stop the simulation. I'm going to mark this whole thing carefully. There we go. And I'm going to I haven't done there. Okay, this is what I want. And I'm going to go edit, copy, click somewhere else, edit, and paste. And it's going to come up, and we're going to place, basically we just copied that. All right, now some lines are copied, so I'm going to erase it. So we have a copy of the same thing. We have another JK flip-flop, and basically set up the same way. So the asynchronous inputs are at 0, so it lets the synchronous they let the synchronous inputs to take over. Both of them are sitting at 1, which means every clock change there's going to be a toggle on the outputs. And we're going to feed the clock not from the clock source, but we're going to feed the clock from the output, from the Q output of the first one. Right? So guess what is going to happen on this output? This output here divides this frequency by half, and this output here divides this frequency by half when it toggles. So basically this frequency is going to be quarter of what this one is. This is fun. All right, let's just connect some channels of the scope. It likes it that way. Okay, cool, no problem. And then, so that's channel 1 as it was, and we're going to connect channel 2 of the scope to the output of the second one. All right, let's see. And now we're going to have 3 channels. Channel 1 is going to be the clock input, channel 2 is going to be output of the first one, and channel 3 is going to be the output of the second one. See if this is a quarter frequency of that. So take this frequency, 1 kilohertz, divided by half, we should have 500 hertz. And then divide 500 hertz by 2, if we should have 250 hertz over here. Well, let's try it. Okay, start simulation, and we only see 2 channels, so let's turn on channel number 3. Oh, we see something, so let's bring it down, position it down, and there we go. It's tough to turn the knobs. Now it's displaying too big, so let's just make it a little bit smaller. And now the triggering, let's just bring the trigger, position it somewhere to a manageable level here. There, so it's nicely visible. And we're going to call up the trigger menu, and we're going to take a sample of this one, of this channel 3, because it doesn't look like it wants to settle down. So change the source for triggering channel 3. Oh, and we just have the trigger here. So all 3 signals are settled down. Okay, well, look at this. This frequency is half of that, and this frequency is half of that. Look at that. This is amazing. All right, so let's measure the frequency. I'm not going to measure that one because we already did. We know what this one is. Let's see if this one here is should be 250 hertz. If this is 1 kilohertz, half of that is 500 hertz, and half of this one is going to be 250 kilohertz. Sorry, hertz. Okay. So the signal repeats from here, it goes up, it goes down, it starts going up here, so this is the period here. So we're going to bring up our measuring cursors from here to here. Or you can just get the division, time per division, and you can do the calculations based on that. But since we can do this with the measuring cursors, we can, why not? So measure, and we're going to measure, let's get the cursors, measure, call up the cursors, and we're going to have that of channel 3. So let's click that, channel 2, no, channel 3, there we go. We have those 2 magenta kind of cursors appearing, and these 2 controls are going to move left and right cursor. So let's bring it up to where 1 begins, all right, here. It's tough to get it right on the spot. Ah, there we go. I think we got it right here where it begins, and get the other one when it starts going up. There we go. I think I got it. Oh, look at this. It shows 250 hertz, and this is 1 kilohertz, 1000 hertz, 500 hertz, 250 hertz. All right. So here's the frequency, here's half of that, and here's half of that. You can keep dividing the frequency down as much as you want just by adding those JK flip-flops. Ladies and gentlemen, you have just experienced a JK flip-flop as a frequency divider.